So what is the radius of our sphere? Wasn't it 3?
3.
So the volume for us is going to be 4/3 pi and then 3 cubed. So 27.9 is 36 pi. So we want to take 36 pi and we want to subtract that. About 95. About 95 cubic inches, 95 cubic feet, 95 cubic kilometers, whatever it is, again, your units are. All right? This is our approximate answer. Now, just for show, I'd like to show you what would have happened had we not broken that up. Okay, had we just gone from 0 to pi and not broke it up pi over 2 and doubled it. So if you double it, because remember we have to do top and bottom, and you go 0 to pi instead of pi over 2, and where we run into that weird thing with the inequality, and we run it through, what do we get? Get the same answer. Why? Why do we get the same answer? Why in the world do we get the same answer? Let me see if I can explain it. 1 o'clock? 2 o'clock? Okay. So if we were to make that inequality be true, we would have to flip the order of integration. Right? So we would have to, instead of doing 0, r, and then that 2 cosine theta, we'd have to flip it so that the negative is now on the left and the positive is on the right. Do you all understand what I'm saying? If we're just looking between pi over 2 to pi. So we already know we went from 0 to pi, right? Pi over 2. But if we go from pi over 2 to pi, what we need is our radius has to actually be like this now, right? This has to be backwards so that the negative number is smaller than r, which is smaller than 0. Y'all with that? But why is this not mattering? Because what happens when you flip the order of integration? What happens when I take an order of integration and I flip it over? What happens to the integral? It becomes negative, doesn't it? It becomes negative, right? You all agree with that? Okay, so what's going to happen here, and this, I'm really stretching here, but I don't want to work this out by hand. When I do my first integration here, right? When I do my first integration, whatever that is, I'm going to get a bunch of stuff with r's in it, right? I'm going to get r's in it. Okay. Then I'm going to replace every r with what? Cosines, right? And then I'm going to integrate again. And what happens when you integrate cosines? What do you get? Sines, right? And sines are what types of functions? Odd functions. So if I have a negative outside, remember, because I'm going to flip the order of integration, when I push the negative in, all that happens in my sines is that that negative sign changes what's inside the argument. What is it? We know sine that is equal to sine of negative theta. That's what it means to be odd, right? So it's like when we flip this, we're flipping the order of integration, but because we wind up with sines, it's not going to matter. I don't think this is explaining it well enough. It has to do with the even and odd properties of the trig functions that we're using. Because look, we're getting the same answer, right? Yeah. Okay, so that means that we're not flipping it over when we're supposed to. But flipping it means that the the negative doesn't matter, which means that when we integrate that, we probably get cosines in it. Yeah, let me try and think through this a little bit more, just so that I have a more clear explanation. We did it, right? We got the right answer? Yeah. This is just to show you that if we had done it this way and overlooked that part, we would have still got the same answer. But it would have been only because of the property of the cosine and sine in there. So I'll try and clarify that a little more next time. We're done though. We're done on this part. And I think we are done with the section. Yeah. All right, that's it for 12.3. Enjoy the homework. All right, 12.4. Time for some applications. We're not going to do a whole lot of applications of double integrals, but we're going to do one that is easy to visualize. So you may or may not have done this in Cal 2. I have a little visual for you here. I have my best, this is the best isosceles triangle I can make out of cardboard. All right, this is the best I could do. All right. So this is what we refer to as a lamina. I want you to imagine this as being a two-dimensional sheet of something. All right, we've got this two-dimensional sheet of something here. So we have to kind of think that this does not have thickness to it. All right, this has no thickness. It's just a sheet. That's a lamina. And what we're interested in doing is finding the center of mass of this lamina. So where is the center of mass? You understand what the center of mass is? Yeah. It's essentially you take a complicated shape. When you find its center of mass, then you can look at the entire shape as just being a single point. And then it makes a lot of things a lot easier if you just look at this as being a point instead of some weird shape. So to find its center of mass, we can actually do this physically by, well, I'll show you. Do you have any idea where the center of mass of this should be? Yeah, so if I give you an equilateral triangle like this, I tell you these sides are equal, do we all agree that the center of mass should be somewhere in the middle like that? But as far as how high up and down it is, it just kind of depends on how tall and narrow this is. Do you all agree? So my center of mass should be somewhere in here. Probably lower than higher because there's more mass down here. We all okay with that? Okay, so now what I'd like to do is show you a demonstration on how you can do this. I'm going to do it with that in a second, but let me do something else first. Brought some little visual aids. I'm going to make another lamina that's going to have a weird shape to it. So that's a weird shaped lamina, right? To find its center of mass, what we do is we kind of imagine like punching a hole in it, like this. I got to make sure it swings pretty okay there. And then what I'm going to do is I'm going to hang this plumb line from it like this. Come on, get off of there. I got the hardest markers to frickin' open. Okay. So I drop a plumb line and I draw a straight line right here, like this. And then what I do is I pick another point. I do the same thing. Oops, it hit my finger. Shit. Stop it. Good enough, all right? Draw another one. And where those two intersect should be the center of mass. Now, if I do a third one, that'll just give me a little more confidence in it. So I can try a third one. And that's pretty close, right? I don't know. I made it close. I made it exact. Right? So there's my center of mass. Okay? So we should be able to do that with this and be able to come up with a center of mass, something like that, right? Okay, so here we go. So this is not, seems a little bit off. Okay, I'll just draw that right there. Oh. So maybe it's not going to be perfect, okay? What the hell? Give it one more. here. Something ain't right. Well, my method's working pretty good. Wait a minute. This seems all jacked up, doesn't it? It's non-homogeneous. See all my paper clips on the back? See all these paper clips? I've moved the mass around, okay? This is correct if this is homogeneous. If the shape you're looking at, if we assume that the density within the shape is uniform, we call it homogeneous. But if the density is non-homogeneous, then your center of mass does not have to follow what you think it would be, right? So this is an example of a non-homogeneous lamina. So what we imagine is that at every single point on this shape, the density is different, right? The density is different here than it is here. There's more mass packed into that point than there is over here. Do y'all understand that? With this, the mass at every point is the same. Big difference. Cal 2, I think I do this. In Cal 3, we can do this. So we can handle, in Cal 3, we can handle both of these. This is easy. This is the trivial case. And we'll talk about how we do the trivial case. But our goal right now is to be able to find the center of mass of a non-homogeneous lamina. Did that trick you? I was trying to hide those paper clips. Did I do a pretty good job? I wasn't being overly, okay. All right, so a couple of things we have to talk about first. You know, what's a lamina? Well, there's a lamina. Remembering that density, the definition of density is mass over volume, or sorry, that is, but we are going to call it mass over area when we're talking about a lamina. So if you take the mass and divide it by if you take the mass of this whole thing and divide it by its area, then that would be your density. That's how we're going to define it. So suppose the density or mass per unit area is variable, meaning the density at every point in the lamina may be different. Then the total mass of the lamina is the sum of the mass at infinitely many infinitesimal rectangles. So what we imagine doing is we're saying, look, we can't talk about the mass of this we can't talk about the mass of this lamina because the density at every point's different. So what we do is we cut it into a bunch of infinitesimal rectangles and we find the mass of each rectangle and then we add them up, right? That's what you would do. Okay, so let's talk about this little infinitesimal rectangle. Well, we know its area. What would its area be? Well, if we're looking at this as being x and this as being y, then the area would be the little change in x times the little change in y. This all looking familiar? Okay, so the area, right? The area of this little thing we will call dA is dx dy. Okay, so we got the area. Now, do we know the density? Well, density is mass over area, right? Which means if I solve for mass, it's density times area, right? Mass would be density times area. And I know a formula for the area. The area is dx dy. The only thing I don't know is the density itself at each point, unless somebody gives that to me. If somebody tells me the density at each point, then I have a function. That function, which we call a rho of xy, is what we call our density function. So if we want to add them all up, we have to do a double integral over d, which is the region, of the density function times the area. So this really means density times area. This will give you your total mass. Now, the important thing to note here is that for me to be able to tell you the mass of a non-homogeneous lamina, somebody must provide me with a density function. I must be able to determine the density at each point. Once I have that, I can tell you the mass. Once I can tell you the mass, I can find its center of mass. But that's down the road. Let's first start with mass. So this is the big formula right here. Somebody provides you a density function, right? Somebody gives you density at each point. Then to find the mass of the total lamina, you just do the double integral over d, which is the lamina itself, of the density function. Now that double integral should look mighty familiar to you. Isn't it just this? Isn't that's all it is, except instead of using f, I'm using rho, right? What does this double integral represent? Like visually, geometrically, what is this? What has this been for us? Volume. The volume underneath f, right? Underneath this surface f, on top of this function d, or on top of this region d. So the way you can actually kind of visualize this, and I tried to do this the best I could on the next example. We'll get to that. Is by, I'm going to show you the visual of this, but let me give you our first little example. A lamina is formed by the region bounded by these curves. So I give you some curves, that creates a lamina. Then I give you the density function. The density function is x times y. Find the total mass of this lamina. So let's look at it. Let's look at it visually, then we'll do it all by hand. Will we? Hold on. It's that one I have the visual for. Darn it. Okay, so I guess we're gonna have to do it by hand. All right, so let's get our lamina. Let's draw it. Our lamina is bounded by y equals 1 minus x. That's a line. Y equals 1, horizontal line. X equals 1. Do you all see the lamina? Okay, our lamina is right here. The density function is xy, x times y. So we want to know the mass of that, right? The mass of that lamina. So I'm going to just ask you this real quick. What is that? What is rho 1, 1? 1. That means that if I go to the point 1, 1, the density at that point is what? What's the density there? It's 1, right? Now, let's go to another point that's in here. How about 1/2, 1/2? That point is right here, right? What's the density there? 1/4. It's not as dense, right? And then I could do, well, this one's going to be, this isn't going to make sense actually. It's kind of weird that this problem is coming from a book, but what's the density there? 0. That doesn't make sense, does it? To have 0 density means you have 0 mass, right? Or undefined. So let's ignore that. Let's act like that didn't happen, okay? Because that would happen here and here, right? But the main thing to kind of see here is that what's happening in this corner is that you have a lot of density, right? So you got more mass out here. Here it's less dense, right? What about along this edge? What happens along this edge? Your density down here is very small, right? Because it's going to be, x is 1, right? So that's 1. So all that matters is your y coordinate. As I move up, the density gets bigger. Same thing happens here. It's not dense at all, and then the density grows to 1. And something like that is happening here also, right? Understand? Okay, so I can't believe I don't have a visual for this. I'm kind of pissed off at myself about this. I thought I had one right here. So when in doubt, or when we run into a problem like this, we'll just do one real quick. So I'm going to just plot x times y. And I want to plot that, just a small little region of it, so we can see it. Oh. So my little triangle is like right in this area, right? It's like right in that little area right there. That's my triangle. I'm looking above that. My density function is basically this surface, except that this surface has no meaning in terms of the lamina, other than this is a, oh, that you can't see that good at all, can you? It looks way better on my computer. Yeah, whatever. Guess what I'm trying to say is that this, when you plug in 1, 1, when you plug in 1, 1, it spits out 1, right? That's coming out at us in the z direction. That 1 that it comes out has no physical meaning in terms of the lamina. That's a measurement of the density. But you could look at it as a surface above this. Does that make sense? And so what we're doing is we're trying to find the volume under that surface, because the volume under that surface is really adding up all of the masses together and then giving you a total mass. If that doesn't make sense, don't worry about it. We'll just keep going. All right, so there's my region, my lamina, and now I just need to set up the double integral over d of rho of xy dA. So when you look at this region right here that we have on the ground, that's a type 1 region. Type 1 I think would work real good here. We don't need polar. It doesn't have any circles in it, so let's stay away from polar. So all I'm going to do now, figure out my restrictions on x and y. So what about x?
It's from 0 to 1.
0 to 1, and what about y?
Y is greater than 1 minus x.
1 minus x here, and less than 1. So what we have here is our little rectangles are going in here like this. So we have the bottom function is this one, 1 minus x. Our upper function is 1. And so all this becomes is this, 0 to 1, 1 minus x to 1. And what are we actually integrating?
Xy.
xy. And then d what? d what?
dy dx.
dy dx. Okay, and that double integral, whatever that value is, gives you the total mass of that lamina. Okay? So to calculate the mass of a lamina that is non-homogeneous, that has a density function given, all we do is we do the double integral over the region D, which is the lamina itself, right, of the density function with respect to area. Whoa. I didn't go back all the way, did I? So this concept can be extended. If you don't want to talk about the mass of a lamina, you can use this in another application, which has to do with what's called electrical charge or charge density. So let's say, again, we have a lamina. And let's say that there's some way of measuring the charge density. So we're talking about like electromagnetic charge. So we're not talking about mass anymore. We're saying at every point that there's some sort of electromagnetic charge here. Then we can find the total charge on the entire lamina by adding up all the charge densities, which is exactly the same as adding up all the little densities times areas, and you come up with the same exact double integral. It's the exact same thing. Except instead of using rho of xy, right? sigma of xy. So do you see that the same integral has two completely different meanings? Yes? It's either a mass or it's a total charge in this case. All right, have you ever heard about, we're talking about centers of mass here. We haven't calculated the center of mass of anything yet, but have you all ever heard of something called a moment or a moment of inertia?
Yeah.
Yes? Okay, so these are physics terms. So when you talk about a physical object's moment about the x-axis, then what you're actually talking about is this. The moment of a particle is the mass of the particle times its directed distance from some axis. So if I have some object here, let's say this is again two-dimensional. Let's say this is my x-axis. If I wanted to calculate the moment of that point, it is the mass of that point times the distance from that point to the x-axis. That's called its moment. And there's a way that we can calculate the moment of the entire lamina. Instead of doing the whole point, we can find the moment of the entire lamina, which should just be, let's see if these formulas make any sense at all. The moment of the entire lamina about the x-axis would be this. Why? Why is it that? Well, what does this computation give you? What does that little piece right there give you? That gives you the mass of this little patch, doesn't it? Like take that little infinitesimal rectangle, and that right there gives you the mass of that little rectangle. And then what does multiplying it by y give you? Well, what's y? Isn't y the distance from here to here? Wouldn't that be y? And so by definition, if you take a particle's mass and you multiply it times the distance from that mass to the x-axis, that is by definition the moment about the x-axis. And if you add them all up, that's your double integral, you get the moment of the entire lamina. Right? So our calculation for the moment is this, about the x-axis. Now what changes if you do it about the y-axis? So I put this lamina here, and I want to do the moment about the y-axis. This is my y-axis. I still have this same piece, right? I calculate the mass of that little patch, but now my distance is from here to here, and that's a measurement of x. So the moment of the lamina about the y-axis is x times the density function times the little areas. Now, you don't necessarily need to know that so much, but you have to know those in order to find the center of mass. The center of mass, by definition, is this. So here's our lamina sitting here. It has a non-homogeneous, it's a non-homogeneous lamina. We would like to find the point. We would like to find that point, which we call x bar, y bar. We want to know what that is, the center of mass. The center of mass is, by definition, the x bar, which is a number, right? This number right here is capital M sub y, which is the moment about the y-axis over the mass. Okay, what is this? The moment about the y-axis? That's this double integral, isn't it? It's that. And what is mass? What is the mass of the lamina? Well, that's another double integral, isn't it? This mass is actually the double integral over d of just the density function with respect to area. So if you wanted, like if I were to give you, this is the way the formula appears in the book, all right? But if you wanted a formula that has all the double integrals in one place, here's what it is. It's the double integral over d of y rho of xy dA divided by, oh, my division bar is way too high there, divided by the double integral over d of just rho of xy dA. You have to, in order to find x bar, you have to do two double integrals. One that calculates your moment, and then you want to divide it by its mass. That's what you have to do. That only gives you x bar. To get y bar, you have to do the moment about the x-axis divided by the mass. So you're actually going to have to do three double integrals to find the center of mass of a non-homogeneous lamina. You have to get moment about the y-axis, moment about the x-axis, and you have to get the mass, because mass is used in both. All right, are you ready for a final example? This should do it. We have 10 minutes, 11 minutes. Let's see how this goes. I hope that this picture will kind of help you see what I was talking about earlier with that surface. Here we're trying to find the center of mass of a region bounded by these curves if the density function is rho of xy equals x squared, and that's it, x squared. So I have a picture below of the lamina. And do you see how it gets darker as you go to the right? That's me trying to represent that it gets more dense as you move to the right. Because what's the density function? I had it up there. Density function was x squared. And so the y coordinate has nothing to do with it, right? The density has nothing to do with the y coordinate. It's just the x coordinate. So if I go, let's say to 1, if I go to 1 on x, any point on that line is going to have the same density, right? Every point there is going to have the same line, same density. It's going to be 1. And if I go out to 2, anything on that line is going to have the same density, which would be 4, wouldn't it? Because that's just 2 squared. But if we pop this out of 2-dimensional space and put it in 3-dimensional space, that's a visual representation of that density. So as you move to the right, you can see the higher means more dense. Does that make sense or not? Okay. So that's why this integral works the same way. If we look at that as a surface, we're trying to find the volume under it. It's exactly that double integral that we're going to calculate. All right, let's get to the problem. Let's start by drawing the lamina. X is 0 is the y-axis. Y equals x. That. This right here. Let me solve that real quick. This is y equals negative 2x plus 6. So that has a y-intercept of 6. That's going to be up here, isn't it? Slope of negative 2, so down 2 over 2. So let's make this 3. So down 2 over 1, down 2 over 1. I think I'm hitting right here. I could find that point, I could double check that point of intersection, right, by setting them equal to one another. Where do they intersect? Set x equal to negative 2x plus 6. 3x is 6. I'm going fast because I only have a few minutes. So this is 2 right there. So that is where they hit. And so my region, my lamina, is this piece here. It's my lamina. So we need to calculate a few things. Let's get the mass first. The mass will be equal to the double integral over d of rho of xy dA. So we need to look at this as a type 1 region. What are the restrictions on x? What are the restrictions on y? So how about x? 0, 2? And what about y?
Y is greater than x.
Greater than this one and less than
2x.
That one, right, which I solved over there, negative 2x plus 6. Right, so it's a type 1 region. And so to do the mass, all I'm going to do now is set this thing up. I'm going to go 0 to 2. I'm going to go negative 2, no, I'm going to go x to negative 2x plus 6. And I'm integrating what? X squared dy dx. And that will give me mass. Agreed? Do it quickly here. 0 to 2, and then we got negative 2x plus 6. The bottom one is x. We're just doing x squared, and we're going to go dy dx, and you get 4. Okay, so this integral comes out to be 4 after you do all the work. Okay? All right, now that's mass. Now we're going to need that, but now we need to figure out what the moment about the x-axis is. So the moment about the x-axis, or let's do this. Well, we need them both. So do y'all want to just go get them both right now?
Yeah.
Okay, let's just get them both. We'll do the moment about the x-axis first. The moment about the x-axis is the double integral over d. The only difference is what? Instead of just this, it's what?
Multiply by y.
Multiply by y. So it's the opposite of what we're looking for. Moment about x, we put y here, then rho of xy dA. So everything's going to set up exactly the same as this. The only difference is instead of having x squared, we're going to have yx squared. What is it? Yeah, x, negative 2x plus 6. Now, x squared y dy dx. Okay, I'll do that on the computer in a second. The other one is going to be the moment about the y-axis, which is the double integral this time over d, but it's x rho of xy dA. And so all that changes is we throw an x in here next to x squared, so it's x cubed dy dx. That should be pretty easy for me to edit up here. So y times 48 fifths. After, not yet, I'm going to use it in a second. I'm just calculating them right now. Okay, so we have right now that our mass is 4. Our mass is 4. Our moment about the x-axis is 48 fifths. And our moment about the y-axis, which is that one, is 24 fifths. Okay? So what's x bar? Because we have a formula for x bar.
The moment of y over the mass.
Yep. So x bar, by definition, is the moment about y over mass. So the moment about y is 24 fifths, but then you're going to divide that by the mass, which is 4. So this is 24 over 20, which is, I can't do this. 6 fifths, thank you, which is about 1.2. Well, not about. It is 1.2, all right? So 1.2 is the x-coordinate of our center of mass. Now the y-coordinate. The y-coordinate is the moment about x over mass, which is 48 fifths over 4. Wow, did I do that? I did that actually. Okay, whatever. What is this, 12 fifths?
Yes.
Okay, 12 fifths, which is 2.4. So where is that center of mass then? It's at 1.2. Yeah. So it's at 1.2. 1.2 is somewhere around there, and then I go up 2.4. So 1, 2, 2.5, 2.4. Somewhere around there is our center of mass for this non-homogeneous lamina. I believe there's a problem like that on your take-home. No? Is there a center of mass problem?
The last one asks about center or moment of inertia, I think.
Oh, moment of inertia, does it?
I think so. I only skimmed through it, but I remember seeing this.
Oh, yeah. Okay, yeah. So that's the next thing. I didn't get to it. So then we have moment of inertia as the next computation. So the moment of inertia in the last 10 seconds, moment of inertia is a number that we use to measure. Pay attention to this because this is on your take-home, all right? The moment of inertia is a number that we use to measure the resistance of an object's motion when you try and rotate it about an axis. So here's the way I want you to think about this. If I take this right here, say this has some mass to it, and let's say I try and rotate it around this axis right here, then it's going to require some sort of force to rotate it around like this. Okay? Understand? Okay. The moment of inertia is a number that represents how much resistance there is. So if you have a very large number, then that means that it doesn't want to get moved around that axis. So would it be harder for me to rotate this around this axis like this, or would it be harder for me to rotate it around this axis from here? The bigger one. So it's the analogy is this. It's kind of like, no, that's not a good analogy. Let's pick up next time. It's 2:40. I think you have enough to get you going for the weekend. We'll get a fresh start on moment of inertia when we come back. That's what's on your take-home test, moment of inertia. But it's a very similar thing here. Yes, question?
So on one of the first examples that we did for this, it asked to find the total charge.
The total charge. Yeah, I know. When I did that, I accidentally brought up the wrong example. See, the example 1 says find the total mass. Okay? And then when I went and I moved and I came back, the next problem is the exact same lamina, but instead of giving you a density function, give you a charge density function. So the computation is exactly the same. It's just your answer is no longer mass, it's total charge. So I'm glad you saw that, but I'm trying to give you two examples that make you do the same computation, but have two completely different meanings in terms of the answers. Does that clarify? Okay, I'm sorry about that. Got a little carried away, I think.